Okay, great. Hi, everyone. Thanks for coming. And it's a great pleasure to speak here. And thank you, organizer, for the invitation. So I'm Xiaowu, and I will give this talk joint with my colleague Saad from UCSB. And this is a joint work with Lisa at Berkeley and Marjorie Shimon at NetPro, and also Jeff from One Concern. And we want to identify risk factors for the cardiovascular disease, use a statistical method, especially the causal inference methods. So I will explain why every study in the cardiovascular disease are super important nowadays. So let me start to give a quick brief overview of the cardiovascular disease. So the CVD is now a leading cause of death in the world. It's not only a problem for the developed country, but also a big problem for developing country. Like, for example, in United States, there are about 5% population have the CVD. And for some developing country, like in the Africa, there are about more than 10% population has a CVD. And the United Nations has officially recognized that cardiovascular disease is a major concern for the global health. And they propose that the identification of the CVD, especially some risk factors, can be intervened at the individual level, the most important health concern. So to be specific, we want to identify risk factors from 4 classes. So the first is the most general, called the demographic risk factors, including age, gender, and the race. However, this class of risk factors is very hard to intervene. And the second we call the lifestyle, which would be more ideal to intervene, such as the smoking. And the BMI is the index for the obesity level, and there's a diet, such as the low-carb diet. And also like alcohol, whether drinking alcohol could be a risk factor. And the third class, we call them the comorbidity, which is simply to be some other disease happens simultaneously with the cardiovascular disease. And we want to know whether, for example, the type 2 diabetes, which I've seen in some patients who also have the CVD, can be a risk factor to cause more severe CVD. And the last class, which were not included for in this first 3 classes, but also important, we include them, such as blood pressure or blood lipids, and also some genetic informations. More interestingly, we also want to study the stress from the working environments. So we want to have a systematic statistical framework to identify which of them are important for causing or reducing the CVD. And here, one motivation is we don't want to have a spurious correlation. For example, there is a famous study by Harvard, a group of Harvard scientists. They find that first, for a group of the controlled patients, they find that HDL is associated with the CVD, especially higher level of HDL positively associated with a lower CVD risk. But when they do the study for another group of the controlled randomized control study, they find that if a drug targets on increasing the HDL, that does not significantly change the CVD risk. So these two put together simply mean that the HDL is some indirect factors for the CVD. So it's not a causal effect, a risk effect for the CVD. Our approach instead, we want to focus on some causal study causal analysis from the observational data. And we want to get some statistical significance. So we also do some subsampling techniques to infer the p-value from our causal inference study. Okay. And here is another interesting example to illustrate the correlation does not mean causation. The left plot has x-axis is a ratio of protein over the weight. So basically indicates how much protein a person takes. And the y-axis means the systolic blood pressure. And the left plot says more protein a patient takes, then the lower blood pressure a patient would have. So this is quite counterintuitive. And indeed, if we do the subgrouping according to their BMI indicating the obesity level, we can find the positive correlation between the protein intake and the blood pressure, and which show in the right plot. And the right plot is more intuitive. And we call such change of the sign of this correlation the Simpson's paradox. And it makes us need to be very careful when should we conditioning on the some confounding factors such as the BMI, and to make the correct causal inference. So this is an illustration from the Julia Pro's book in 2018. It says like associations on the bottom ladder, and any conclusion from the association study cannot infer anything about the intervention or the counterfactual inference. And what we like is to do the second ladder of the intervention, or even the top ladder of the counterfactual, to answer the question of why and also the if. So the causal inference in the CVD are not that common. What we can find in the literature are the studies on the Mendelian randomization. The idea is the genetic information in patients are randomized, inherited, so they can take advantage of this genetic randomization to study some risk factors. Indeed, they find that alcohol intake is a big risk factor, and the LDL cholesterol also will cause the CVD. And our focus will take a different approach. We want to focus on demographic and lifestyle, the risk factors for CVD, and the demographic or the lifestyle cannot be inferred from the randomization in the genetic information. Instead, we can only infer from the observational data. So we will show how can we do that. And our motivating example is whether the obesity will cause type 2 diabetes. And we take an approach called the potential outcome framework proposed by Neyman and Rubin. So we can see the first step, we have some ideal causal graph, which is a directional graph in mind to represent what's underlying causal effect. And here's the BMI, the risk factor index obesity level, and the outcome is whether a patient is type 2 diabetes. And the confounding factor includes the gender and the age, which had the impacts of both the BMI level and the T2D. So we call that confounding factor. And the second step is we want to have some ideal estimate of what we mean by the effect of the risk. And here we use the potential outcome, which is an expectation of Y1 conditioning on X. So 1 here means the treatment or the obesity level equal to 1. and the Y1 means outcome if they receive this treatment, which is obesity. And the minus expectation of Y0, 0 means control group, which is not obesity. And the expectation of Y0 condition, also the X, basically conditioning on the gender and the age by controlling the gender and the age. So we get something called the average treatment effect. And here we kind of want to get this estimate, potential outcome estimate for both the individuals in the treatment group and the control group, and take the average. So that means average treatment effect. And the third step, we have some new method to infer the p-values, whether the potential outcome is significant or not. And here's the key step, which is a second step. We apply a method called the match method based on the propensity score. For example, if I want to estimate the expectation of Y0 conditioning on X, so how can I do that? The idea is I project the original high dimensional data on both control and the treatment to a one-dimensional line using some function. Here we use a propensity score, which takes a form, looks like the one of the 1 plus exponential to minus x beta to do the projection by project the multidimensional x to the one-dimensional pi. So we can measure the distance between the points. And if we want to see what's the expectation of Y0 condition X for the control group, I only need to group the treatment patient with the control patient and look at their sample difference to get the estimate for the potential outcome. So same logic apply for the people in the treatment group. So we take the average and they will get the average treatment effect. Okay, and so what the data we use are the first-hand clinical data from UK, which will help us to infer some clinically evident the result. So the data consists of like 256 subjects in North UK. However, there is a difficulty. This is a time series data with 2 points, and at the time 0, so everyone will take no low carb diet, and at type 0, no low carb diet, and step 1, everyone will take the low carb diet. And this is unusual time series, basically saying there's no control group which will take the low carb diet at the 2 points. So will cause a big problem in our inference. And but however, luckily we have all kinds of the measurements on the subjects, like the weight, height, BMI, and all the lab results. So the Saad will continue to explain how we use this data and with our new method to infer the results.
Thank you, Xiaowu. So yeah, given this kind of unusual and not convenient data structure, we propose a method called randomization. So of course, it's motivated by the fact that we have 2 time observations. One is the so I don't actually see the slides anymore. One is the observation at time t equals 0, which assumes that it's when the individual did not take the treatment. And yeah, no, I see them. And the second one is at time t equals 0, which is observed after a period of time. This period of time can actually be can be different between subjects. And during this second consultation, we assumed that all individuals have had the treatment. So the idea then, because one of the important assumption that is violated by taking the whole data set is the stable unit treatment value assumption, or also called the spillover. So if an individual is observed at two states, then there's actually, by structure, a spillover effect on the data. So we use subsampling for that to mimic a randomized experiment by taking either one of two observations or one of the observations of the two individual from the kind of 2n length vector of observations, which leads us to 2 power of the length of the subsample of the sample kind of subsamples. And we repeat the subsampling a number of times to take a kind of Monte Carlo estimator by taking the average of all the average treatment effects of each subsampling. Then we are interested in the significance of the average treatment effects, and to do that, we obtain a p-value for each subsample by doing a permutation test, which consists of replacing the treatment vector by a noise vector from the same distribution. So this is kind of an outline of how we do that. I won't actually go over it, but just emphasize the main the main steps. Yeah, we kind of permute. We kind of randomly select a index of the individuals and randomly select with probability 1/2 either the first or the second time period. We then estimate the average treatment effect by the method described by Xiaowu, which is the propensity score matching. We then apply a permutation test in order to calculate the average number of individuals that fall within the tails of the distribution to test for the null hypothesis of no treatment effect, or that the average treatment effect is equal to 0. And then we take the average treatment effects for each subsample as our estimator, and either an average of the p-values observed for the different subsamples, or look at the distribution of the p-values to assess the significance of the test. So the first question, simple one, that relies on a simple DAG is, what is the effect of obesity on type 2 diabetes? So for that, we take the DAG where BMI is the treatment, type 2 diabetes is the outcome, and we control for gender, age, and LCD. Why do we control for LCD in that case? Is because, we have 2 time steps, so we want to avoid having the LCD kind of impact the BMI in our experiments. Because the potential outcome framework requires the treatment to be binary, we set 4 BMI categories: normal, overweight, obese, severe obese, and then we test for each low risk versus high risk BMI categories, which means normal is the control group, or T equals 0, and overweight is the treatment group, T equals 1. Or that we take overweight versus obese with the same setting, or obese versus severe obese in the same setting. And for type 2 diabetes, we have no diabetic, non-diabetic, pre-diabetic and diabetic. We see in the table on the right bottom that the average treatment effect is positive for all three categories, with actually being higher for the normal versus overweight ones. So this is actually suggests that BMI indeed increases the risk of type 2 diabetes, with even increasing that risk by 50% for the normal weight versus overweight. The p-values for this particular case is significant, which also suggests that the impact is significant. Okay, the second question is related to low carbohydrate diet, which was the main purpose of the study in decreasing cardiovascular disease risk. So here we take a little bit a more complicated diagram, take a little bit of time to explain it. So we have gender and age impact BMI, type 2 diabetes, and CVD risk. We have type 2 diabetes impact CVD risk, and we have BMI impact type 2 diabetes, CVD risk, and we assume that LCD impacts BMI, type 2 diabetes, and CVD risk. So it means that it impacts CVD risk through BMI and through type 2 diabetes. And here we talk about indirect effect, or it directly affects CVD risk. And here we talk about the direct effects. The total effect is the sum of these two, and we are interested in the three effects. So to do that, we need to, type 2 diabetes here is called a mediator. So it means that it kind of mediates the impacts of the treatment onto the outcome. And for the CVD risk measure that we take is the Reynolds score, which is an aggregated risk measure for cardiovascular disease that takes into account HDL, LDL, total cholesterol, systolic blood pressure, age, smoking habits, etc. And we actually find that all the total direct effects and indirect effects are negative, suggesting that LCD in all cases decreases the risk of CVD risk. We also find that the p-value in this case is in the significance range. So from this data, at least, we find that LCD decreases the risk of cardiovascular disease. So we kind of apply the same process to different cardiovascular disease factors known in the literature as the type 2 diabetes, systolic blood pressure, LDL, total blood cholesterol. And we actually see that in all the increasing factors that LCD decreases these by actually a negative average treatment effects, and it increases HDL. So 10 seconds to conclude. We developed a randomized method for causal inference for CVD. We found that BMI is indeed a high risk factor, and that LCD can significantly lower CVD risk.